Good morning, students. Once again, welcome back to session 4 of Banach spaces class. So here in this class, we will discuss about the sum of subspaces, or in other words, a Banach space can be split as sum of subspaces. So look here. Suppose we have a Banach space, say B. B is a Banach space with the same norm with this one. Okay. Now suppose M and N are linear subspace of B such that B can be written as the direct sum of say M and N. So B can be written as the direct sum of M and N. You know how to define the direct sum of any two subspaces. You have learned it in vector spaces. Okay. Then what will happen? Any Z vector Z belongs to B can be written as sum of an element of M plus sum of an element of N, where X is an element of M and Y is an element of N. Okay. So now if I define a new norm on the linear space B by norm of say Z dash Z, is the new norm, okay, which is defined like say norm of Z whole dash is equal to norm of X plus norm of Y. If I define like this, then say B dash is the same set B with the new norm dash, this one. Can this is a norm on B, and B dash, that is B with this norm, is a Banach space if M and N are closed. If M and N are closed. This is the thing that we will discuss in this class. Means if B is a Banach space with the norm, and suppose B being written as a direct sum of its subspaces M and N, then any vector Z in B can be written as Z is equal to X plus Y, where X is an element of M and Y is an element of N. So then suppose the new norm is defined like this: norm of Z dash is equal to norm of X plus norm of Y. Then the same set B with the new norm, can this be a Banach space? So what are the conditions on this to be a Banach space? This is M and N are must be closed subspaces of B. So first let us look at proving this is a, in fact, norm dash. This is I denoted by norm dash is a norm on B. Norm on B. So first condition is what? The first condition is, now since this is a norm on B, so we have norm of X. Norm of X is always non-negative. Norm of Y is also non-negative, because X and Y belongs to M and N, means X and Y belongs, they are elements of B itself. Therefore norm of X is greater than or equal to 0, norm of Y is also greater than or equal to 0. Therefore norm of X is greater than or equal to non-negative, norm of Y is non-negative, means their sum norm of X plus norm of Y is also non-negative. Norm of X plus norm of Y is non-negative, means according to our new norm, so norm of Z whole dash is also non-negative. This is the first condition, right? Second one, suppose norm of Z with respect to the second norm is 0. This happens if and only if what is the norm defined? So norm of X plus norm of Y is 0. So norm of X, norm of Y, these both are non-negative things. That sum is 0 means each must be equal to 0. So norm of X must be equal to 0, and norm of Y must also be equal to 0. Norm of X is not equal to 0, norm of Y is equal to 0 means, according to definition, X is 0 and Y is 0. If X is 0 and Y is 0, then certainly X plus Y is also 0. X plus Y is also 0 implies, what is X plus Y? X plus Y is nothing but Z is 0. Thus we have proved norm of Z is 0 implies Z is equal to 0. This is the second condition of a norm. Let's come to the third condition. What is the third condition? Norm of Z plus Y is less than or equal to norm of z plus norm of, so this is the condition 3. See, suppose you take here z1 and z2 are elements of b dash, means z1 is equal to x1 plus y1 and z2 is equal to x2 plus y2, where x1 and y1 are elements of m and y1 y2 are elements of n. Okay, then what will happen? You consider norm of z1 plus z2. Norm of z1 plus z2 is what? Norm of, say, x1 plus y1 plus x2 plus y2. So if we group up the like terms, say x1 plus x2 plus y1 plus y2. Now this is looking like norm of x plus y, but norm of x plus y, this is totally with respect to the second norm, right? So if it happens, what will happen? This is equal to norm of s, this is equal to this is equal to norm of x1 plus x2 according to our definition plus norm of y1 plus y2. So, and suppose I will write a bracket for this. But norm of x1 plus x2 is less than or equal to norm x1 plus norm x2. Norm of y1 plus y2 is less than or equal to norm y1 plus y2 because this is a norm on B. Okay. So let's look at this. What will happen? Say this is less than or equal to norm x1 plus norm y1, sorry, norm x1 plus norm x2 plus norm y1 plus norm y2. Okay. So again you group these terms. So this is equal to what will happen? Say norm of x1 plus norm of x1 plus norm of y1, okay, plus norm of x2 plus norm of y2. So this is equal to what? Norm of z1 dash plus norm of z2 dash. Therefore norm of z1 plus z2 dash is less than or equal to norm of z1 dash plus norm of z2 dash. So this is the condition, third condition of a norm. Let's verify the fourth condition. So now the fourth condition is, let z1, let z be any element of b dash. So z be element of b dash means z will look like, say, x plus y, where x and y are elements of m and n respectively. So let consider some scalar alpha be a scalars. Then norm of alpha into z whole dash. Norm of alpha into z whole dash is equal to norm of alpha into x plus y. Okay. So this is linear property you can use. So alpha into x plus alpha into y. This one. Now alpha x is an element of m, alpha into y is an element of n. Therefore use this property of a norm, new norm. So this is norm of alpha x plus norm of alpha y. So but this is again mod of alpha into norm of x plus mod of alpha into norm of y. So this is equal to mod of alpha into norm of x plus norm of y. So this is equal to what? Mod of alpha into norm of z whole dash. Thus we have proved norm of alpha into z whole dash is whole dash means I am saying dash means this is a new norm. That's all. Okay. This is equal to, we have proved that it is equal to mod of alpha into norm of z dash. Therefore say the same set B with respect to this norm, new norm, is a norm linear space, that we return it by B dash. B dash is a norm, B dash is a, what you can say, norm linear space. Okay. So next, the next condition is, our main condition is, so we need to show, say B dash is complete if M and N are closed subspaces. So to prove any completeness of any space, what we do is here, say we will take any Cauchy sequence in B dash, say Zn is a Cauchy sequence, Zn is a Cauchy sequence in B dash. If Zn is a Cauchy sequence in Z dash, then each element Zn will be look like, say, Xn plus Yn, okay, where Xn is an element of M and Yn is an element of N for each N. This holds, right? So now, by definition of a Cauchy sequence, what will happen? For each epsilon positive, there exists a positive integer, say n naught, such that m comma n greater than or equal to n naught imply norm of Zn minus Zm is less than epsilon. Norm of Zn minus Zm means, so we write the value of Zn is Xn plus Yn, Zm is Xm plus Ym, and if you this becomes norm of, after rearranging the terms, Xn minus Xm plus Yn minus Ym, so it is less than epsilon. So this is nothing but, this is the element of M and this is an element of N, so this can be written as norm of Xn minus Xm plus norm of Yn minus Ym is less than epsilon. So sum of these two terms is less than epsilon means each of the terms must be less than epsilon, because both are non-negative terms. So Xn minus Xm is less than epsilon, and norm of Yn minus Ym is also less than epsilon. So norm of Xn minus Xm is less than epsilon, Yn minus Ym is less than epsilon for every m comma n greater than or equal to n naught implies what it says. Xn is also a Cauchy sequence in M, Xn is a Cauchy sequence in M, and Yn is a Cauchy sequence in N. This becomes the Cauchy sequence in M and N respectively. So, but M and N are closed subspace of a Banach space B. Every closed subspace of a complete space is also complete. Therefore, M and N are complete. M and N are complete means every Cauchy sequence in M and N are converges. Therefore, we can say Xn converges to, say, X belongs to M and Yn converges to Y belongs to N. Now Xn converges to X belongs to M, Yn converges to Y belongs to M means what will happen? Say there exist integers n1 and n2 such that there exist positive integers n1 and n2 such that n is greater than or equal to n1 implies norm of x1 minus x is less than, say, epsilon by 2 by definition of a convergence. And similarly, n is greater than or equal to n2 implies norm of Yn minus y is also less than epsilon by 2. So this is definition of a convergent sequences. So this implies, I will take, say, n naught I will take to be the maximum value of this, maximum value of n1 and n2. If I take n naught to be the maximum value of n1 and n2, and I'll set z be the element in B dash with the sum x plus y, then what will happen? Then for n greater than or equal to n naught, we have norm of Zn minus z. Norm of Zn minus z is equal to what? Norm of Zn is xn plus yn minus z is x plus y. So this is equal to norm of xn minus x. I am grouping the terms in terms of m and n separately. So plus yn minus y. So, but this is equal to what? By definition of a norm, which we have considered xn minus x plus norm of yn minus y. But this is less than epsilon by 2 and this is less than epsilon by 2, totally which is equal to epsilon, means norm of zn minus z is less than epsilon, Norm zn minus z is less than epsilon means what? Zn converges to z. Therefore, we have considered a Cauchy sequence Zn in B dash and we have proved that Cauchy sequence converges to the element Z which belongs to B dash. Therefore, we can say B dash is complete. So, if B dash is complete, then it becomes a Banach space. Okay. Now, let us look at another example. Say, suppose M is any linear subspace of a non-linear space or Banach space X. If M is a linear subspace of a non-linear space X, then the closure of M, this is the closure of M, you know how to write, this is the closure of M. Then the closure of M is also a subspace of X. We need to show closure of M is also a subspace of X. So, to show a closure of M is also a subspace of X, what you have to show? If I take any two elements, say X and Y belongs to M closure and alpha comma beta scalars, then the linear combination, what is the linear combination? Alpha X plus beta Y must belongs to M closure. Alpha X plus beta Y belongs to M closure. Now, by the definition of the elements in M closure, see here X and Y are in M closure means they are adhering points. By the definition of adhering points, what will happen? For every neighborhood of X contains a point of M which is nearer to M, or for in every neighborhood of X contains a point of M, or in other words, every neighborhood of X contains a point of M means the distance between the point of X, the distance between X and the point of M is very small. Okay, very small. Or in other words, we can say every neighborhood of X contains a point of M. Okay. So, what will happen if X and Y belongs to M closure? Correspondingly, we will have the points X dash comma say Y dash belongs to M such that norm of X minus X dash is certainly less than some small number, say that I will take to be epsilon by 2 times mod alpha, and similarly norm of Y minus Y dash is also less than epsilon by 2 times mod beta. Okay, this is for our convenience I have taken. This is some number, small number. Okay, so now, so to have the element alpha X plus beta Y to be in M bar, so what is the condition? The distance between this element and the element in M must be less than a small number which is usually taken to be the epsilon. So consider the distance. Now, norm of alpha X plus beta Y, the element of M dash, M bar, and you consider the element in M. Say this is alpha X dash plus beta Y dash. This is the element in M. You consider the distance between these two. So this is as usual norm of alpha into X minus X dash plus beta into Y minus Y dash. So according to definition of a norm, this is less than a norm of alpha into X minus X dash plus norm of beta into mod beta into norm of Y minus Y dash. Okay, here I split it out. I will take outside directly. Now less than or equal to mod alpha into norm of X minus X dash plus mod beta into norm of Y minus Y dash. This is less than mod alpha into, what is norm of X minus X dash? It is less than, so epsilon by 2 times mod of alpha plus mod beta into epsilon by 2 times mod beta. So this gives the mod epsilon get cancelled, mod beta gets cancelled. This is less than epsilon plus by 2 plus epsilon by 2, that's equal to epsilon. Means the distance between the element of m bar and the distance between the element of m is less than epsilon. Means this element is in the neighborhood of this one. Okay. So what we can say, therefore m bar is also a subspace of X. Subspace of X means the closure of a subspace is also a subspace of X. This is a small result and it's important also. Now let's come to the definition that we already discussed. Say you know that when X and Y are into nonlinear spaces, then the mapping, say T from X to Y, is said to be continuous if for every sequence xn in X converging to the point X, the sequence T of xn in Y converges to T of X, For every sequence xn in X converging to X, the sequence T of xn in Y converges to T of Y. This is the definition of a continuous function T. Okay, and also say suppose we have two nonlinear spaces, say X and Y. Say suppose we have a mapping T from X to Y. Then we say this mapping T is bounded map. T is said to be a bounded map or bounded map. Then if T is said to be a bounded map, if there exists a real number or positive constant k such that norm of T of X is less than or equal to k times into norm of X. Norm of T of X is less than or equal to k times into norm of X, then we say T is a bounded map or bounded. In other words, since T is defined on they are vector spaces, so means they are linear spaces, therefore we can say the T is a bounded linear map or bounded linear transformation. Okay. So now we are going to prove one of the important theorem of this session. So that theorem says, say look at this theorem. So suppose we have a T is a linear transformation T is a linear transformation of a nonlinear space X into another nonlinear space Y. Then the following statements are equivalent to one another. What are the statements? The statements are looking like this. See, first one is T is continuous. If says the same, if X and Y are any two nonlinear spaces and T is a mapping from X to Y, then we have the following conditions. First one is T is continuous. Second one is T is continuous at the origin. Continuous at the origin means same. For every sequence xn converges to 0, the T of xn also imply T of xn converges to T of 0. What is T of 0 is 0 itself. Okay, this is the second condition. So third one is T is a bounded transformation. T is a bounded linear transformation is the third condition. And the fourth condition is, so if I take S to be the closed unit sphere in X, say if I take, what is the closed unit sphere means? It contains set of all X belongs to X such that norm of X is less than or equal to 1. It is a closed sphere in X. Then its image T of S. What is the image of S means? T of S is a bounded set in T of S is a bounded set in Y. We have to show T of S is a bounded set in Y. First is T is continuous. The four conditions are, first is T is continuous at the origin, T is bounded, and the set S, which is the unit sphere, closed unit sphere in X. This is, if S is the closed unit sphere, then its image is a bounded set in Y. So these are 4 equivalent statements that we need to prove it now. Say first one, what's the first condition? Say I will prove like this. So the way of proving this is, so we can show that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1, or in the words 1 if and only if 2, 2 if and only if 3, 3 if and only if 4. I will use this later condition. Say 1 if and only if 1 if and only if 2. 1 if and only if 2. So means I will assume 1 and I will prove 2. So what is 1 means? Suppose T is continuous. We need to show T is continuous at the origin. T is continuous means what will happen? Let xn be a sequence in X such that xn converges to 0 as n tending to infinity. Since T is continuous, what will happen? If xn converges to 0, by definition of a continuity, because it is continuous at every point of x, therefore this implies T of xn converges to T of 0. But T of 0 is 0. This implies, what you can say? This implies T of xn converges to 0. Thus xn converges to 0 implies T of xn converges to 0. Therefore, you can declare that T is continuous. T is continuous at the origin. T is continuous at the origin. Now, conversely, you assume T is continuous at the origin. So, conversely, you assume that T is continuous at the origin. So, we need to show T is a continuous mapping. So, let xn be a sequence in X. Let xn be a sequence in X such that xn converges to X. Xn be a sequence in X such that xn converges to X. If xn converges to X, means xn minus x definitely converges to 0. Xn minus x converges to 0 means T of xn minus x converges to T of 0, because we have assumed that T is continuous at the origin. T of xn minus x converges to 0 means, so this implies T of xn minus T of x, because T is a linear mapping, converges to 0. This implies T of xn converges to T of x, means T is a continuous. T is continuous. Okay, understand? Xn converges to x implies T of xn converges to T of x. Therefore, we say T is a continuous mapping. So, we have proved 1 if and only if 2. Let's come to 2 if and only if 3. So, what is 2? 2 if and only if 2 means 2 is saying T is continuous at the origin. We need to show T is a bounded map. T is continuous at the origin. T is continuous at the origin, and we need to show T is a bounded map, right? T is bounded map. So suppose, if possible, suppose that T is not bounded. T is not bounded. Okay. Suppose T is not bounded means what? We do not find any number k such that norm of, we do not find any number such that norm of T of x is less than or equal to k times into norm of x for any x. This holds for any x. For any element x belongs to x. For any element x belongs to x. Means we do not find such number such that this holds for every, not for any, for every x belongs to x. There may be this such number exists for 1 or 2 elements, but not for all elements. Okay. Then what will happen for each positive integer n? Then for each positive integer n, certainly we will find the corresponding vector, say xn belongs to, for each positive integer n, we find a vector in x such that norm of T of xn is certainly greater than n times into norm of xn. Definitely this happens. Okay. So if this is the case, then this implies that 1 by n into norm of xn is 1 by n into norm of xn into norm of T of xn is definitely greater than 1. Okay. So since this is a scalar, I can bring it inside the norm. Therefore, norm of, so directly I will take T of xn by n times into norm of xn is greater than 1. Okay, understand now? So now I'll set this xn by n times norm of n as yn. Say yn is equal to xn by norm of xn. Xn by n times into norm of xn. Then what about norm of y? Then norm of yn becomes, so norm of xn by norm of n into norm of xn. So you know that the value is this equal to 1, but 1 by n. So 1 by n tends to 0 as n tending to infinity. So 1 by n tend 0 as n tending to infinity. Therefore, what you can say, yn converges to 0 as n tending to infinity. Yn converges to 0 as n tending to infinity. But norm of t of yn is what? Norm of t of yn is greater than 1 for every n. Now yn converges to 0 means if it is continuous, then norm of t of yn must be converges to 0 here, but norm of t of yn is greater than 1 for every 1 means t of yn does not converge to 0. Although yn converges to 0, t of yn does not converge to 0. But this contradicts our assumption that t is continuous at the origin. Okay, we have assumed that t is continuous at the origin, so this is a contradiction. Therefore, why this contradiction arises? Due to our assumption that t is not bounded. Therefore, t must be bounded. Okay, understand this? So we have assumed that t is continuous at the origin, and we have shown that t is bounded. So converse part. So conversely, you assume that t is bounded. Say conversely, you assume that t is bounded. You show that t is continuous at the origin. T is bounded means norm of t of x is less than or equal to k times into norm of x for every x belongs to x. Let xn be any sequence in x such that xn converges to 0. What to show? T of xn converges to 0. So now as norm is a continuous function, xn converges to 0 implies norm of xn converges to norm of 0. Norm of 0 is 0 itself, means norm of xn converges to 0. But we have assumed that norm of t of x is less than or equal to k times into norm of x. This holds for every x. So this holds for every x means xn's are points of x only. Therefore, norm of t of xn is less than or equal to k times into norm of xn according to our assumption, because t is bounded. But what will happen here? Norm of xn converging to 0. This is converging to 0. If it is converging to 0, what you can say? Norm of t of xn is converging to 0. Norm of t of xn is converging to 0 imply that t of xn itself is converging to 0. Thus, if we assume that xn converges to 0, we can see that t of xn is also converges to 0, meaning thereby t is continuous at the origin. Okay, so this is 2 if and only if 3. Next, let us take up 3 if and only if 4. What is 3 now? 3 is this one. 3 is bounded. T is bounded implies the image T of S is bounded set in Y we need to prove. Okay, suppose T is bounded. T is bounded means again, so this is norm of T of X is less than or equal to K times into norm of X. This holds for every X belongs to X. Now, so let X belongs to S be arbitrary. Let X, you take X to be any element of S. Element of X means according to definition of S, norm of X certainly less than or equal to 1 because it is a element in a unit ball. So norm of X is less than or equal to 1 means according to this convention, what will happen? Norm of T of X certainly less than or equal to K for every X belongs to S because norm of X is less than or equal to 1. So this is for every x belongs to S. Now norm of T of x. What are T of x? T of x are elements of S where T of x lies. If x belongs to S, T of x belongs to T of S. It is in turn is contained in Y. Okay. For every element, look here, for every element of Y or belongs to T of S, norm of T of x is less than or equal to K means what you can say, the set T of S is bounded. It is bounded by the bound which is K. Therefore, T of S is bounded in Y. Okay. Now conversely you assume that T of S is bounded. So we have to show T is bounded. Okay. Now T of S is bounded means just now what we have shown, norm of T of x is less than or equal to K. This holds for every element x belongs to S. Okay. This holds for every x belongs to S. Now let us take say x dash to be any element of arbitrary because we need to prove for the general case, means for any element let x belongs to x let x dash belongs to x be arbitrary. Then if x dash belongs to x is arbitrary, then x dash by norm of x dash by norm of x dash certainly belongs to S. Why? Because norm of x dash by norm of this one, norm of x dash by norm of x dash, this one is certainly is equal to what? 1. For any element whose norms is 1 means that element belongs to S. If that element belongs to S, then for every element in S we have this condition, right? Therefore what you can say, norm of T of x dash by norm of x dash is less than or equal to K, right? Now norm of x dash is a scalar that can be taken out of the norm. So this is 1 by, this implies 1 by norm of x dash into norm of T of x dash is less than or equal to K. Since this is a non-negative quantity, so we can non-zero quantity here, so this we can transfer it to this side. This implies norm of T of x dash, so this is equal to less than or equal to K times into norm of x dash. Norm of T of x dash is less than or equal to K times norm of x dash. This holds for every element because in x, because x dash is an arbitrary element of x. So this holds for every x dash belongs to S. What you can say then? Therefore, by definition of a boundedness, T is bounded. So here we have proved theorems like, conditions like, say T is first is T is continuous, then T is continuous at the origin and T is bounded, and the image of the unit sphere is bounded set in Y. These are 4 equivalent statements. One important thing we can observe from this theorem is here the equivalent conditions. The equivalent conditions are T is continuous and T is bounded. They are all equivalent. This is a very important theorem. T is continuous if and only if T is bounded. So in future, in the next coming theorems, so whenever if we require to prove some transformation is continuous, it is enough to show that T is bounded. Showing boundedness is a little bit simpler task compared to the continuity. So in future, whenever we are going to show T is continuous means T is bounded. So on a non-linear space, boundedness and continuity are equivalent. On a non-linear space, boundedness and continuity are equivalent. Means that the transformation is continuous implies it is bounded, and the transformation is bounded implies it is continuous. This is a very important note of this class. Thank you.